Well, now I let our speakers do the presentation. Juan Carlos and Pablo, the floor is yours.
Thank you, Fernando. This is Pablo Benitez. Let's get started on our topic of today, which is high concentration photovoltaics, potential and challenges, particularly focused on optics. This is the outline of this webinar, and we will start with a brief discussion about why high concentration photovoltaics is important. The interest in high concentration photovoltaics comes from the fact that the world record efficiencies up to date is being done by the multi-junction tandem 3-5 solar cells, which have already proven efficiencies about 40%. With these very high efficiencies, what is relevant is that we would like to have or to take advantage of them. It's also relevant the speed at which such increase of efficiency is being produced in the last decade. The problem of these cells for being used for electricity generation in terrestrial applications is their cost, that they are around 2 orders of magnitude above the cost of conventional silicon cells. The way to compensate that cost is the use of concentration photovoltaics, and that's the reason why we're talking today about that. The concentration allows to reduce the area of the semiconductor, and this is a brief schematic drawing of what's going on with a concentrator photovoltaic. On the left we see a flat panel conventional PV module, while on the right we see a concentration PV module in which an element, which is the optical concentrator, takes the sunlight and concentrates it onto a smaller solar cell area, which could be the high efficiency solar cell. The final goal will be to reduce the cost of the produced electricity, and this cost has to be with 4 items: the cell cost, other costs, the solar radiation, and the efficiency. The cells, we have said that are more efficient, but they are also of much higher cost, in fact much more higher than the efficiency increase. And then the only way to compensate that is to introduce the concentration, and that's the reason for it. But other elements in this equation are affected too. First, the efficiency will not be that high because we will use the optics and has a optical efficiency which is not 100%. There are also other costs that will be associated to the use of concentration, as the tracker or thermal management, etc. And also more accuracy may be needed, and affecting the solar radiation. Only direct radiation is useful for high concentration systems, and that could be a significant percentage of the global radiation. Let us introduce some fundamentals of concentrator optics, and for that we will use the example of the most common PV concentrator, what is an imaging device. This is the classic PV concentrators are based on imaging optics, and for the example we have selected the flat Fresnel lens. An imaging concentrator essentially makes a mapping between the sky and the cell. So when the light impinges normal to the lens, it will focus onto the center of the cell. And when the light is tilted, the rays are tilted, they move on the cell. And the acceptance angle is the angle at which the rays approximately focus on the edge of the cell. And this acceptance angle gives us an idea of the tolerance of that system, and we will call it the tolerance angle. As we will discuss later, it will not affect only the tolerance of the tracking, but the tolerance of the all manufacturing and in general the tolerance of the system. The formal definition of acceptance angle is a little bit more detailed than that. And in reality, for instance, the Fresnel lens is not a perfect imaging device, and it has both geometrical and chromatic aberrations of the rays. That means that the ideal transmission curve versus incidence angle is not perfectly sharp, but is more smooth as shown on the left. And usually acceptance angle is defined at the angle at which the transmission drops to 90% of that of the maximum at normal incidence. Another simple concept to have in mind is how you can modify for a given concentrator, for a given imaging classical concentrator, how can you modify the concentration factor? Assume you take the lens that we were showing before and you just put a cell which is double in length. That will mean that the tolerance angle, as we defined before, will be focused approximately will be approximately double. So what is a basic rule of thumb for an imaging concentrator is that if you double the cell side, you can double the tolerance or the angular tolerance of the system. So that product is constant, and such a constant strongly depends on the optical design concept. That means that if you use other type of concentrator, like based on a mirror or a more complex system, in general this equation applies for that family, but the constant that you have on the right may be very different depending on the concept. These are a few examples of some of the systems that are now commercial based on flat Fresnel lenses. This has been taken from websites. We can see from Amonix, Wascore Photon, Concentric Solar, MCore, Sol3D, Rima, Renovalia. All these are just examples. There are many other companies that are making products based on flat Fresnel lenses. It's the most popular concentrator optics. If we would use just a Fresnel lens on a cell, that some companies do, but assuming that we do it, we find from the explanations that we have seen that there is a trade-off with the homogeneity and the tolerance angle. Assume that we have this situation that is shown in this drawing, and the sun angular diameter is about half a degree. Since we are imaging the sky onto the cell, that means that if the imaging formation would be perfect, we will have the image of the sun on the cell when we are perfectly aimed. And when we moved, the tolerance we were talking before is obtained when we have slight mispointing, so the sun image moves around the cell. So we see that for this situation, which is this perfect imaging is not a clear case, but what we see is that there is some compromise that if we want to have more pointing tolerance, sorry, if you would like to have a higher tolerance, you will need to increase your cell, and then the non-uniformity will be worse. This is one of the reasons why other optical elements are usually used in classic photovoltaics, and one way to solve it is using, for instance, a homogenizing prism, also called kaleidoscope. This substitutes the cell with a prism that will uh, confine and guide the light toward the cells put in a lower position, and then the entry of that prism will act as a virtual cell to be illuminated by the primary lens. There are other examples of classical non-emitting secondary optical elements. One of them is that element could also provide concentration to the system in order to further reduce the cell area. This is the case of that, for instance, CPC type non-imaging concentrator. And in order to compare these two systems that we are showing here, apart from the issue of the homogenization of the light, we should think about the two systems such that the two have different type of receivers. And these two receivers, a large cell and a small cell with a secondary optical element, as the CPC, should be compared in terms of the cost of that element and efficiency. There are other examples of imaging concentrator designs. For instance, the parabolic mirror shown on the left, or a two-mirror Cassegrain as the ones shown on the right. There are also other examples of companies using this kind of optics. For instance, on the left we see the system of solar systems, which has a big parabolic dish illuminating an array of cells at the focus, or the two-mirror Cassegrain of cell focus shown on the right. Let's talk a little bit about more advanced optics for high concentration photovoltaics. And the first question is why advanced optics could help. First is that they have the potential of obtaining higher efficiency, especially at systems level, higher tolerance, and if needed, high concentration. And these three items to be improved need to be achieved without increasing the number of optical elements in order to keep efficiency high and cost low. Secondly, it would be possible with advanced optics to make each optical surface perform as many functions as possible, as concentration, homogenization, etc. And if you decide to use a certain concentration level that has to be with your cell cost, it would be the best option to have the highest tolerance in your system to maximize the efficiency at systems level. Well, when one designs a system and is working on it, may think if more tolerance is needed or not. And we can try to find a list of symptoms that indicate that you may need more tolerance. For instance, if you have already developed a product, but making the optics require a very high accuracy, well, that means that if you would have a different design with a more tolerance, which is more tolerant, you will be able to reduce the optics accuracy. So this is first symptom. Second one is that your assembly is expensive due to the need of fine adjustments. Third, your efficiency decreases significantly when you make a single unit and go into an array due to optical mismatch. And fourth, the efficiency increases significantly when you increase your cell size. That tolerance in your system is not only that it's only associated to the accuracy of your tracker or the accuracy even of your control system of your tracker, but has to be shared between or among many other items. First of all, it's obvious that the sun has a certain angular extension, and you have to take that into account. Second is that the optical component manufacturing needs some tolerances for shape and also for surface roughness, surface shape and roughness. Also the intramodule assembling. And these two elements are usually for instance, in a mature industry as automotive, in the range of 0.1 to 0.5 degrees for the optical components in it. But it's not only that, you need also more to share your tolerance budget with other elements as the array assembling and installation, the tracker structure stiffness, and the tracking accuracy, which includes not only the electronic accuracy, which can be very good, but also the accuracy of your mechanics, the gears, etc. Well, the most advanced optics at present for concentration photovoltaics are based on what are called free-form optical surfaces, which are surfaces in which you don't force the rotational symmetry, the classical rotational symmetry or linear symmetry, and they have no prescribed symmetry. This gives you degrees of freedom to the design and allow to perform multiple functions in a single element. The most advanced method in the field of non-imaging optics to design freeforms is the one we work with, which is called the SMS 3D. This is an example of a freeform device which we call XR, which is composed by a mirror and a lens. And that lens includes also a homogenizing prism, which is very short. This system has already been, recently been published experimental results of it. And this is another example, which is a free-form design of a Fresnel lens and a secondary optical element. In this example, which we will call a Coulomb design, in which we perform what is called Coulomb integration or Coulomb homogenization, is one example to show that it's possible to produce multiple functions in a single element. And in particular, the prism is avoided in this system, providing homogenization without that prism, just by the freeforms. This is how it's performing, which is significantly different from conventional. And we see here that the homogenization, that's the radiant distribution of the cell on the cell, is very good with no prism. These are just two examples of CPV systems which have a particular configuration. This is just another example taken from another application, which is solid-state lighting, which shows a different device, which we call RXI, making also freeform or even freeform cooler integration in this ultra-compact device. Let's continue this talk comparing different high concentration PV systems, particularly to establish how to compare them. The final criterion to compare them would be the cost of the electricity. The problem is that it's very difficult to evaluate that cost before the product is already mature and has been in the field for many years, which is not the usual case in most CPV systems under development. Instead of evaluating or trying to evaluate the full cost, it's usual to select several parameters which are considered important for the final cost as merit function in the comparison. Such parameters could be many, and there are some in this list here. We are highlighting the first three, which are the module electrical efficiency at nominal conditions. Those nominal conditions may be discussed, so it is not too clear what to select. The concentration, also the tolerance angle. We could also talk about the power per unit area of the model or per area of the cell of energy production estimated in certain locations or other items. We're going to select three of them that we consider that are relevant for the final cost of the energy, and would be these three first. And we could represent these three items, efficiency, concentration, and tolerance, in a certain three-dimensional space. And then this means that if we take one example, for instance, Fresnel lens, with these parameters, an electrical efficiency of 27%, concentration of 400x, and a tolerance angle of plus minus 0.5 degrees, we would get that that concentration system is represented by a point in this space with those coordinates. That space or three-dimensional space has boundaries that are given by the thermodynamic limits. For instance, electrical efficiency can't be bigger than 86% according to thermodynamics. This is for the case of using infinite junctions in the multi-junction solar cell. The thermodynamics also applies for limits in the concentration and the tolerance. So the product of concentration times the square of the tolerance is limited by n squared, which is the refractive index of the capsulant surrounding the cell. And this gives a certain region of that space which cannot be violated. In this drawing, we are seeing in real scale what is the situation of the Fresnel lens concentrator with respect to those boundaries. And what is remarkable here is that that 27% is still far from the very, very top limit of 86%, but it's also not close to the other limit of concentration and tolerance. It's also remarkable the fact that this point is not too far from the sun radius, and that could affect significantly the cost of the system. Let's compare, for instance, these two systems. The one mentioned before of the advanced XR freeform concentrator that has already proved a 27% electrical efficiency, and a Fresnel lens concentrator which has already proven also the same efficiency level. But the other two parameters, concentration and acceptance angle, are very different in both systems. So represented in this space, we can see the differences here we have that the concentration is higher, so fewer cells are used or a small cell area. But what is more significant is that the tolerance of the XR is much better than that Fresnel lens concentrator. Once you have a design family or a design concept, as we mentioned at the introduction, is it possible to redesign your system for that family, making that you can vary the concentration and vary the tolerance accordingly? And then what happens is that you can move along that line that is shown there, for instance, for the XR, to provide a different design for different concentration and a different tolerance. And following this rule, that it means that we can set a same type of system to provide us the same concentration level at the Fresnel of 400, but with a close to plus minus 3-degree tolerance. But if one prefers to use another point along that line, for instance, we could go there to set a concentration factor of 2000 and still have a tolerance which is significantly higher than the Fresnel lens concentrator. Here we have taken several published data of different concentrator designs from different manufacturers, and we have set them here in this chart for comparison. We are not, this is an example of one of the systems corresponding to one of the points in that cloud. And in order to see it better, we're going to represent two of the projections of these point clouds in this graph. So on the left we show efficiency versus tolerance, on the right efficiency versus concentration. And when looking at it, especially in the 3D space that is not shown here, we can distinguish the advanced XR concentrator providing these points, which has already proven high efficiency, electrical efficiency. And as we can see here, is not only superior to most of the others in efficiency, but especially superior in tolerance and concentration. So this is why advanced concentrator optics can help in with respect to classical ones. Here is the present status or the present situation. Setting a target, we think that a reasonable target for next years would be to focus on increasing the efficiency and also slightly increasing tolerance and concentration, but still is not completely clear what is the concentration level which is the optimum. So we could, it's possible to change the target following the curve as before that we mentioned. So it would be possible to make a target, the decreased concentration level at to 400, but with at to 600, for instance, with a slightly higher efficiency achievable because our tolerance could be as close to 3 degrees as a target. Now, let's now discuss about comparing with the two-axis tracked flat plates. Comparing high concentration photovoltaics with flat plate tracking is not directly possible in the concentration tolerance efficiency space that we were discussing, because they are very different. we should go back to the equation of the cost of the energy to start discussing about the differences between the both systems. It's likely that the two-axis track flat plates are the direct competitor of the HCPV, especially in the short term, because both are using trackers. But let's analyze item by item the similarities and differences. First, regarding the solar radiation, the flat plate collects the diffused radiation on the plane on the aperture, which can add between 15 and 30% or more for energy for flat plates depending on the location. Regarding the efficiency of flat plates is usually rated differently than in the case of HCPV, and that has to be taken when doing comparisons, because as the standard for rating the power of, or nominal power of modules is set at cell temperature of 25 degrees, while it's rated at 20, sorry, there's a mistake there, 20% ambient temperature for concentrators. And the efficiency versus temperature coefficients are very different from the different cell technologies. And what is also very relevant is the fact that flat plate trackers and general flat plate systems and manufacturing don't need the same level of accuracy as concentrators. Taking into account the preceding considerations plus the optical efficiency, the silicon and multi-junction cell efficiencies, we get that at present, when you compare the most efficient systems or examples of CPV and flat PV, the electric energy production per square meter is only about 10 to 15% greater for CPV systems in a sunny place. This means that there is no a great advantage in energy production for CPV, even the efficiency of the cells is higher. And then at this moment in time, it's not a clear advantage regarding the cost of the energy of CPV, produced by CPV versus flat panels when using two-axis tracking. However, what we think is that the most important advantage of HCPV versus flat plates in two-axis trackers come from the comparison and the potential of the comparison of the recent time evolution of efficiency, showing the potential of HCPV. And as mentioned before, the slopes of the efficiency is very different. And in particular, the advances, even in the last year, there have now been improved in cell efficiencies at 1 cents for silicon. And the fact that the silicon cells are much more mature technology, that implies a lower risk, but also less expected improvements. And this also can be considered similarly for the structure of cell costs and in both technologies. The summary of this webinar: the potential of HCPV relies on the fast increase of multi-junction cells efficiency. The near-term challenge is beating the two-axis tracking flat panels, which have already been successfully used in large installations, in particular in Spain. In order HCPV to succeed in this competition, we think it needs high efficiency, sufficiently high concentration, and as much tolerance as possible. Such combination can be best solved by advanced optics. And since this HCPV industry is still in its very first steps, we think it would be important to look for the synergy of this HCPV technology with the present high throughput, low cost industries, such as automotive or solid state lighting. So this is the end of the presentation. Thank you for your attention. We will be open to your questions. And just to make some propaganda, let's say, for further reading, we published with Roland Winston this book on non-imaging optics. And there is also a very nice book from a friend of us and competitor in writing books, which is Julio Chavez, Introduction to Non-Imaging Optics, recently published. Thank you very much.
Okay, good. So thank you very much, Pablo. This is an excellent presentation, very interesting. I guess our audience really appreciate it. So now, the first announcement, presentation will be available on Leonardo Energy website. So you are invited to go there. I'm writing the website. Just 1 second. Yes, so in the Q&A window you will find the link. So this is Leonardo Energy website, which is our website, and then you go to discussion webinars. You will find this presentation, the recording of this webinar, as well as the former webinars that happened in the past. Yep, so now we have some questions. I see also that Mr. Paniatov has a raised hand, so he's invited to submit the question through the Q&A window. So if you want, we can start with now with questions from our audience. Gubadia asks whether HCPV is useful for heating or only for electricity generation. So I send the question to the Q&A window, and then Juan Carlos or Pablo, you're invited to provide an answer. Thank you.
Hello, this is Juan Carlos Miñano. The question is, let me see, I don't see here. What it was, I don't see it, but it was regarding the, I guess it was regarding the use of concentration also for heating. I'm assuming that the question is about the use of the concentrator for both functions, for concentrating the light onto a photovoltaic cell plus heating some fluid. This is some idea that is being pursued by, is an old idea, and there are some companies working with this, and also some researchers. The problem with this solution is that the highest efficiency of cells is got at the lowest temperature, and most interesting temperature for the fluid to leave the concentrator is the highest one. So finally, this is a compromise which in my opinion, does not balance the complexity introduced by the use of this fluid in the concentrator.
Okay, thank you. From my side, I can add that there are some companies working on parabolic trough concept to focus light, and then to convert it into either electricity using low concentration photovoltaics, or keeping the light and then distribute it inside the buildings, or even to produce hot water. Simultaneous production of heat and photovoltaic generation, as Pablo says, is probably not compatible, as the higher temperature you produce, the lower efficiency operate photovoltaic cells. So I'm afraid there is no compatibility of both functions. However, Pablo provided the more precise answer. So now let's continue with the questions. We have several, so we could submit this one. So is high concentration photovoltaic useful for heating only for generation? Sorry, this is the previous one. So who is developing a system with dish and CPV in the dense array method? So the floor is yours, Pablo, Juan Carlos.
And Fernando, just the question is not put in selected question. Could it be put there so we can see it? Is that possible? Or?
Yeah, I hope it's visible on the Q&A window, which is on the bottom left corner.
And the company that has already developed such a system is called Solar Systems. It's an Australian company, and they use a big dish to concentrate on that dense array. That system is commercial, as far as I know, and they are using. They have been using this morning. I think it's Boeing Spectrolab array of solar cells for the dense array, and the cooling is active. So the answer to the question is solar system is the one that I know that is commercial.
Okay, thank you. So the next question, I send it again to the Q&A window. So comes from Carl Swiben. Mr. Swiben states that he worked on CPVs in the 80s. So he has a question concerning heat dissipation and CTE mismatch, if there is still a problem. So his specialty is advanced thermal materials. So what can you say about these mismatching problems and heat dissipation? Thank you.
Yes, there is still the heat dissipation is a big issue of CPV systems, because the reason is the same as before. The temperature decreases the cell efficiency, and the problem of the biggest problem, the bottleneck of the heat flow used to be the contact between the cell and the first heat spreader, and this contact has to be very good from the thermal point of view, but at the same time, in this region, depending on the configuration, there are problems of electrical isolation. So we may have requirements of good thermal contact and and good electrical isolation, and all this makes this area very difficult, and the problems are still bigger when you consider that because the thermal content has to be very good, the CTE of materials which are bonded together has to be also very good. Or has to be very similar. I mean they have to scale at the same time, or to decrease at the same time.
Okay, good, thank you. So we go to the next question. It comes from Patrick Russell Allison. When do you think the first utility scale CPV application will hit the market?
Well, in the case of the installations in Spain, this is Pablo, I would say that the utility scale, I mean, is already there. In the first company in terms of installations is the Spanish one, Huasco Photon, and they have already installed 12 megawatts of CPV. I mean, it's not utility scale, but it's in the path, and I mean, it's not negligible with respect to the amount of flat PV that has been installed in Spain too.
Okay, good. So indeed, in Spain there are a beginning of development on utility scale photovoltaics. So you have ISFOC installations. There is some announcements of Concentrics doing some megawatt scale developments with Abengoa Solar. Huasco Photon is as well doing some solar farms. However, indeed, we still wait for special regulation on concentration photovoltaics to have the final push to this technology. So it's probably coming soon. So we can go to the next question. So it's Kathy who asks how much the optics cost in the total cost of the module. What the portion will be? This is an interesting question, so we'll let the experts. Thank you.
Yeah, it's an interesting question, and it's also a complex one. It depends on the concentration level. I mean, how the budget of cost in the module is shared. Usually is said to be in the range maybe between the 15% and 30% of the cost of the module. But note that also how the optics perform affect the efficiency of the whole system, especially at systems level. So that means that an increase in your efficiency of the global system due to the use of better optics may allow you to use an optic which is more expensive, but the system cost goes down.
Okay, good. So we have now some questions regarding market development and market prices. Well, this presentation focuses more on technology issues. Maybe we can submit a general question to our speakers whether they follow this market development and price development. So I have some questions regarding how fast do you think the market of CPV will develop? Also an announcement on how Solfogius announces the installation of 10 megawatts for 100 millions, which means $10 per watt, which is pretty much higher than flat PV. Well, what can you say about market expectations and price expectations? Thank you.
Uh, well, that's also a very difficult question. We guess that the CPV has been in with let's say a low level of development for a long time, perhaps more than 20 years, and has recently had an explosion of activity, especially in the private sector, and that has been very important because it has make the development go much faster than before. We think that the next 3 to 4 years will be critical for this, for clarifying if the CPV is going to succeed in its niche market or not. And but right now, the situation is that the technology is, and also in general, the CPV industry is very young. And regarding the second question, if $10 per watt is representative, there are so few examples in this market now that we are not talking about a large number of offers and talking about average, which has some statistical meaning. So the answer is it representative? Well, yes, but but also the other costs that have been offered recently are representative. For instance, the installations that several companies, including Solfocus, but also Concentric, Isophoton, have done in the ISFOC installations are also representative. And the official, this is has been a public offering, and the price was at around 6 or 6.5 euros per watt.
Thank you very much, Juan Carlos. Mike Ross has a similar question. What are the prospects, in this line, what are the prospects for reducing the cost of megajoule cells? So what are the guidelines expected for reduction of costs? Thank you.
Well, when looking at publications of the different cell manufacturers, and usually they have some roadmaps. At this moment, they usually say that maybe the cells or cells plus receiver sometimes are in the range between $10 to $20 per square centimeter. And they have a slope to get in the next years below the $10 per square centimeter. But as Juan Carlos said before, this industry is still young, and then the room for improvement, their processes and the learning curves are still in the process. They are changing wafer sizes and automatizing the assembling process. So as far as we know, they have potential for cost reduction, but it's not too clear to what extent. Additional to that is the fact that since they operate at high concentration, what happens is they use fewer cells. So for a given order, the concentration factor plays against them in terms of maturing their learning curve, because they have to produce fewer cells. Well, I would say that.
Okay, thank you very much. So there are many questions. I'm afraid we don't have much time. I will suggest it's now 4 in the afternoon Central European time, so the time allocated is over. So I suggest we continue for 15 more minutes in order to answer to some more additional questions. However, we will publish this presentation, this recording, and also the list of questions. These questions will be addressed online later by our speakers. So let's try to